Okay, so what we're going to do today is do some parallelogram proofs. So we learned a whole bunch of different properties of parallelograms, and you'll probably use most of them throughout all these proofs. A lot of that also has to do with triangles being congruent. Things have to do with parallel lines because we're in parallelograms, etc. So in this particular proof, the first statement is going to be, in parallelogram you can abbreviate as p-gram. So p-gram ABCD and DAPQ. That's given. Well, the fact that you have a parallelogram, you've got so many different properties happening. You're wanting to get BC and PQ being congruent sides, and you should notice that AD and BC are going to be congruent because opposite sides of a parallelogram are congruent, and AD and PQ are congruent for that same reason. Well, if you've got one side congruent to another, and that side congruent to a third, then those first two sides have to be congruent to each other. And that's by the transitive property. So let's see if we can finish this thing up. We know for sure that AD is congruent to DC, and we also know, BC, that AD is congruent to BC, and we also know that AD is congruent to PQ. And that's because opposite sides of a p-gram are congruent. Well, then either transitive or substitution, I will take either. But then if you know that BC and AD are the same, and AD and PQ are the same, then you can say that BC and PQ are the same. Transitive property is the one that I probably would think of, but there's no reason why you could not use substitution, because the fact that you know AD and BC are the same, you can substitute BC in for AD, and you can call it substitution. Either one's acceptable. Okay, so that takes care of the first proof. Second proof. You've got a parallelogram PQRS, you've got a diagonal QS, and you know that PS is more than PQ. Well, PS and PQ happen to be all in this triangle. So if we know that PS is more, we'll call that 10, we'll call that 8. Then you should know that sides opposite those, that angles opposite those sides have to be larger. So let me rephrase that again. The angle opposite the biggest side of a triangle is the biggest. And that's what's going to be very helpful to us here. So we now have your first statement as p-gram PQRS. And with that, you also have the diagonal, which I'm not going to write, but feel free to put it in there. And PS is more than PQ. And that's given. Okay. And then we know, with that being the case, we know that the lines that are on opposite sides of one another, the sides opposite, because you've got a parallelogram, have to be parallel. So basically, this line and this line are parallel because that's a property of parallelograms. So we could then say that QR is parallel to PS, and then we can say opposite sides of a p-gram are parallel. Well, parallel lines tend to give you alternate interior angles, which means that angle Y and this angle down here are congruent. Let's just call this angle 1, just to make it a little bit easier. So then we could say this, that angle 1 is congruent to angle Y, because we know that parallel lines form congruent AIAs. Now we've got angle 1 and angle X being in the same triangle, and angle 1 is opposite the side that's marked 8, and angle X is opposite the side that's marked 10. So we know that for sure angle X has to be more than angle 1. So angle X is greater than angle 1. And the reason for that being is in a triangle, angles opposite the larger side are bigger. and they're bigger than angles opposite the smaller side. Feel free to write the rest of that, but I think this is fine. In a triangle, angles opposite the larger side are bigger. Then what we can say is we're looking for angle x to be more than angle y, but angle 1 and angle y are the same. So we should be able to substitute in angle y for angle 1, and then we can say that angle x is more than angle y, and that is because of substitution. It's really substitution inequality, but if you just put substitution, not a big deal. So make sure you're good with that one. Okay, last one. This one can be done more than one way. Most of these can be done more than one way usually. It just depends on the properties that you want to use of the parallelograms. So let me see if I can move this over. Maybe not. Not wanting me to move. Can I move this? Nope, can't move it. Okay, no big deal. We got quadrilateral MATH. AH bisects MT at Q. So MT is what's bisected, there to there. TMA and MTH are congruent. TMA is here, MTH is here. How do we know math as a parallelogram? A couple of ways to do it. One of the ways that I think I'm going to use, and I happen to use this one a lot, is if you can prove one pair of sides, both one pair of opposite sides, both congruent and parallel, you automatically have a parallelogram. And I bet you I can get congruent triangles in here and be able to do that. So let's see what we can do. We've got quad math AH bisects MT. And then we have angle TMA congruent to angle MTH. So this is all given. We know that from that bisector that MQ and TQ are congruent. And that's going to be definition of segment bisector. Well, we also happen to have vertical angles at Q. So instead of actually having to name them, I'm going to write measures, or I'm sorry, I'm going to write numbers in them. And we're going to say that angle 1 and angle 2 are congruent. So angle 1 is congruent to angle 2, and vertical angles are congruent. Well, now we've got congruent triangles, and we can say that triangle MQA is congruent to triangle TQH, and that's because of angle side angle. Well, then by CPCTC, we can say that sides MA is congruent to sides TH, and that's CPCTC. So I've got this is congruent to that. Can't draw on it for some, ooh, I don't know how that happened. That thing's got to go back up there. So these guys are congruent to one another. And then as it turns out, the fact that I happen to have these angles here being congruent, okay, that actually creates parallel lines, because if AIAs are congruent, then you must have parallel lines. So that would be also saying that MA is parallel to TH. And that reason will be is if AIAs are congruent, then the lines are parallel. That's enough then to complete this whole proof, because if you've got one pair of parallel lines, if you've got one pair of opposite sides, both parallel and congruent, you must have a parallelogram. So we then can say MATH is a p-gram, and the reason here is a quad with one pair of opposite sides, both parallel and congruent, is a p-gram. Now you are done. Again, this is not the only way to do this problem. It's just one way. You can definitely find other ways to do it. This is one of the more straightforward ways that I think, but again, there's more than one way. All right, so make sure you go with this proof. I know this thing is kind of in the way. Oh, I can move that over, even better. Okay, and then you should be good. Okay, good luck with the homework.